from across the river. So Yufei is the only person whom I know reasonably well who won International Mathematics Olympiad 3 times. Well, he got golden prize only one time, right?
Oh, I got twice.
Oh, I didn't know that. Okay. Well, he got golden, bronze, and silver. So
the whole collection.
The whole collection.
Yeah. So he was studying. He got his PhD from MIT with Jacob Fox, who's now at Stanford. He's a graph guy. And then he went to Oxford and spent a year or 2 there, and now he's back over here for a tenure track position at MIT. It's very hard to get. So he is amazingly prolific for the mathematician in his stage of the career. So I've been told that people get positions at a prestigious university having only one paper in archive, if it's a good one. If you're in math, but he already has how many papers? About 40. You know, all the top prestigious journals in math, like Chernoff, probability, and so on and so forth. So he is, of course, the kind of very promising researcher, and we invited him here because he also has some results on a very difficult problem in vigorous theory of random graphs, which is the analysis of the limits of sparse graphs. You know, he has a paper on the so-called sparse graphons, LP graphons, with people also across the river from Microsoft Research, Box and Chase. And also more recently, he had papers on large deviations in sparse random graphs, in particular triangles. And so today, that's what he will be telling us about, everything he knows about large deviations in exponential random graphs. Sparse or not? Maybe sparse. Okay. Good. Okay. You are. Please.
All right. Thank you, Dembo, for the invitation. It's a real pleasure to be here, especially on such a nice day. Everybody coming here. I really appreciate the audience. So I'll talk about large deviations in random graphs and also exponential random graph models. So this is meant to be largely a survey talk. I'll tell you about some of the developments in the past few years. There's been a lot of development on this subject, rigorous mathematical developments, and I'll give you a survey of that. And if you have any questions, I've prepared a lot of slides, but if you want to interrupt me at any point to ask me more about a specific topic, please do so. I want to keep this as informal as possible.
Okay, good.
Okay, I'm interested in, for this talk, I'm interested in asymptotic distributions. Right? And the most classical results have to do with what is the normalized asymptotic distribution. The central limit theorem tells us basically everything we want to know about the distribution of many types of random variables under fluctuations that are on the order of standard deviations around the mean. In this talk, I will focus on large deviations, which has to do with what happens when your random variable is very far away from the mean. And often I will be interested in what happens when x is at least twice the expectation, very, very far from the expectation in terms of the standard deviation. For central limit theorem, there's often this universality. Right? So this picture is an example of universality. You have a Gaussian mean, you have a Gaussian limit. But for large deviations, it's often problem dependent. For a different problem, you can have a very different answer. And so the set of solutions is often much richer, and the kind of analysis often becomes much more difficult. And here are some of the key questions I want to address to some extent, or at least have you keep in mind when it comes to large deviations. First is just estimating the probability. Right? So what is the probability that x is really, really large? And we're talking about very small probabilities, often exponentially small in the size of your system. What does a typical conditioned instance look like? So if x, condition on x achieving this large deviation under this very rare event, what does a typical instance look like? And finally, how would you model, or estimate, or sample such a large deviation event? Suppose I tell you, maybe I don't know a formula for it, but can you use a computer to sample from this large deviation event, or estimate the probability, or sample a random instance? All of these are related problems. I would say much more about the first two, partly because I actually don't know that much about how to do the third one, even though maybe for practitioners it's the most important, most interesting one. I mean, I'll tell you what I know, but actually I think just in terms of rigorous mathematical results, we don't know that much for the third question, even though I think it may be the most interesting question. So as a warm-up, so this is something that you learn in a standard course in probability. If you have a sum of independent, identically distributed random variables, let's say with finite variance, then the classical central limit theorem tells you that if you subtract the mean, divide by the standard deviation, then it converges to norm. The standard large deviation result, one of the first results you see in large deviations, tells you how to estimate the probability that this random variable x, think of this little x as basically some number exceeding the mean. And so what happens when you have x exceeding the mean, let's say by a constant multiple? And the formula tells you that it should decay exponentially, and it tells you exactly what number you should put up there. And this is, in literature, this is usually called a rate function. And this rate function, unlike the central limiter, here the central limiter, I don't care what the distribution of the y's are, as long as if they don't have fat tails or some weird stuff like that, then every distribution has the same limiting distribution. But for large deviations, give me a different random variable y, and I will have a different function I. So for instance, when y is the Bernoulli random variable with probability p, then this is what the function looks like, and that's the standard relative entropy function.
You will talk about how to find I given y?
Yes. So for random graphs, for the application, so not in general. Okay, so this is for a sum of independent random variables, and this is very well understood. And we pretty much can answer any reasonable question that you may have about this classical setting. Now, the thing I want to talk about is the much more difficult question: what happens when you have a sum of dependent random variables? Or more generally, when you have x, that's the function I'm interested in, and I'm interested in understanding, I have, let's say, a sequence y's of IID Bernoulli random variables, and some function f applied to this set of IID random variables. So, for example, f could be a low-degree polynomial. So not just the sum, not linear, but small, maybe degree 3, degree 4 polynomial. And such polynomials capture many of the interesting problems that we consider, such as counting triangles in the random graph. When you count triangles in the random graph, the triangles, we think of the edges, each edge corresponds to a variable, and triangle is a set of triangles. You can write down a cubic polynomial encoding the triangles. This kind of problems is usually much more difficult to solve. Now, there are a few things which you can do that are relatively easy. You can compute moments, often without too much difficulty. For a specific power of k, think k equals to 2, I can compute this expectation, for example, just by expanding out this polynomial and do linearity of expectation term by term. And if you are really good at computing moments, imagine if you compute as many moments as you want, then in principle you should be able to also prove a central limiter. If you have enough moments, this gives you the information about the limiting distribution. Large deviation, on the other hand, this is a whole Wild West. There's no general technique for handling large deviations of such functions. And what I'm presenting in this talk is a special case that's of interest because of graph theoretic applications, where we can do something. We can say something about rigorously computing large deviations. Okay, so here's the specific application that will guide most of the talk. And this is known as the upper tail problem, where x is the number of triangles in the Edis-Rene random graph GMP. So usual thing. And vertices, every edge appears with probability p independently. I can compute some easy quantities, like small moments. For example, the expectation is just n choose 3 times p cubed, where n choose 3 triples the vertices. Each of them forms a triangle with probability p cubed. And if you do, as I mentioned on the previous slide, if you compute moments and some extra arguments, but nothing terribly deep, but if there's some work involved, then one can show that it's possible to show that x converges to the normal distribution when you normalize everything appropriately. So the central limit theorem is known for this quantity. But estimating large deviations, in particular, computing the probability that x exceeds its expectation, let's say by a factor 2, this is notoriously difficult. So there's no general standard method for doing this, and in fact, we didn't even know what is the right order of the log probability until maybe 5 years ago. So, yeah, about 10 years ago. So this is very difficult. But now we know much more, and I'll tell you what we know. So that's the problem again. So this is known as the infamous upper tail. So there's a paper by Jensen and Luchinsky where at the time they surveyed every technique that was available to them at the time. And that still didn't get you the answer. The order of log probability was determined only, this was published in 2011. So this is difficult. Now the proof is not very long, but it's incredibly tricky. It took people a lot of effort to find the techniques that were useful to analyze such quantities.
And what the techniques were?
So it's different from what I will say in the rest of this talk. So here they're only interested in the order, but not the constant. Right? And there they use combinatorial or conditioning type arguments, looking at, take a pair of vertices, and look at what happens when you have too many common neighbors, and very hands-on type arguments. And it's actually unclear. I mean, in fact, in Chatterjee's paper, he says that he had difficulty finding a good name for this method because somehow it's not being as conceptualized as much as we would like it. Okay. On the more intuitive level, let me ask the following question: what can cause, whatever that means, what can cause a random graph to have too many triangles? Right, so we're looking for the probability of having too many triangles. Imagine you are some designer and you're trying to make the graph to have too many triangles. Like, what can you possibly do? So there are a few things you can try. For example, you can increase the overall edge density. If you increase the overall edge density, lifting from GNP to some bigger GNP prime, or some bigger P prime, then that will certainly increase the number of triangles. Some other things you can try to do is, for example, if you have an extra set of edges at your arsenal, you can put down those edges, make a clique, and that clique will generate lots of new triangles. Another thing you can try to do is pick a small set of vertices and form a hub, where every vertex in there is connected to everything else in the rest of the graph. Now this also generates lots of new triangles, because if you take one of your vertices in the hub, look at any pair of its neighbors, then with probability p, those two other neighbors are also connected, so you get lots of new triangles that way. So these are all some of the ways you can get lots of new triangles. And you can ask, what is the dominant reason? If you experienced large deviation, what was the dominant reason for this large deviation? There are some names, okay, and maybe there's some other reason. Okay, so I'll just list some possibilities, but maybe there are some other reasons. So there are names for these phenomena. They come from statistical physics. And the first one is called replica symmetry. So uniform boost everywhere. And then a catch-all for everything else that happens is called symmetry break. Anything that's not replica symmetry. So the question is, what is the dominant reason? What caused large deviation? So let me give you a summary of what we now know and what we believe, right? In the sense that we can prove these things under a certain hypothesis, but the proof in the most general setting is still elusive. Let me set up the notation. X is the number of triangles in this GMP, and we're trying to understand large deviation, X exceeding the expectation by a factor of 1 plus delta. The sparse setting, so let me begin with the sparse setting, meaning that P goes to 0 as n goes to infinity. So the graph, the density of the graph becomes smaller and smaller. Now, I don't want P to go to 0 too quickly, for two reasons. One is if it goes too quickly, for example, if it goes down like 1 over n, then the graph becomes fundamentally a very different kind of, if you have only roughly a linear number of edges, then the behavior is very, very different. But the other reason why I put not too quickly here is that what we can prove is only for P going down to 0, like n to the minus some small number, n to some minus small power. But we believe it should go all the way down to maybe 1 over root n. So this is what we believe, but what we can prove is, I'll say in a second, but with some specific power.
But below root n, you don't have any intuition.
There's some intuition. There's some intuition, but we cannot prove anything close to that region. Turns out it depends on what your delta is. If delta is large enough, then the right thing to do is to plant a clique. So like in the last slide, plant a clique. If delta is less than this 27 over 8, well, delta is always positive. Delta is always a positive number. If delta is less than 27 over 8, it turns out the best thing to do is to plant a hub. So a small set of vertices, every vertex is connected to everything else. Every vertex in this hub is connected to everything else in the graph.
Is it 27 over 8 is like 3 half cubed or something?
Yeah, that's okay. But it's just some number that comes out of the calculation. Yeah, when I say clique, you have to then figure out what is the size of the clique, and that's a fairly straightforward calculation to figure out what is the right size, and then once you do the trade-off, that's where delta crosses from one region to the other. For the dense setting, meaning I hold P to be constant. Here, I will show you some pictures later on, but now I'm just asking the question, do you have replica symmetry or do you not have replica symmetry? But even that question, actually, we do know now what the answer is, but even in general, even just asking, is it replica symmetry, is often difficult. We don't always know what the answer is for other similar problems. How do you compute large deviations? So, there are two main steps. In the first step, I'll call this a large deviation principle, LDP, that reduces the problem at hand to a variational problem. So variational problem meaning some kind of maximization, minimization problem. That the purpose of the variational problem is to model the most likely cost. So trading off a cost versus how likely is this cost will it arise. And then the second step is to solve this variational problem. So both steps are tricky, and many different situations we don't know how to solve one or the other, or sometimes neither. So let me do a review of large deviation. So this is classical theory. If you fix two numbers p and q, p less than q, and x distributes as a binomial random variable, and I just ask what's the probability that x exceeds nq. And we know what the answer is. This is very classical results. Premier's theorem, for instance, tells you that the answer, the log probability, has asymptotics. This number, which is relative entropy or KL divergence.
I was puzzled by that.
And it's this formula, but the specific form is not so important. How I like to think of it is that this is the cost of tilting, in the sense that initially I start with some random variable with density p, and I say I want this random variable to be much bigger. like bigger than p. I want to push it to q. Okay, so I'll let you do that, but you pay me a cost. You pay me an exponential cost to tilt this variable from expectation p to expectation q. And that's the cost that you pay. Okay, so this is how I think of this quantity. And with that in mind, here's how I can formulate this large deviation variational problem. I want to compute the probability that the number of triangles in GMP is much larger than expected for each pair of vertices, each pair ij of vertices. Let me tilt its probability from p to some bigger number, qij. Maybe a different q for every pair of vertices. All right? I push it up. I pay a cost, the same number as in the last slide. I pay an exponential cost to push it up. And my objective is to minimize the relative entropy cost. So to find the most likely cost, I want to pay as least probability cost as I can to achieve what I want, namely to get enough triangles. So starting initially, I'm at GMP, so every edge, every pair of vertices, I think of attaching a number p, and I want to boost everything up. So change each number p to some bigger number so that I have enough triangles. But I want to do this conservatively, in a way that minimizes relative entropy cost. Okay, so that's the variational problem. Now, I've told you this story, which is a nice and hopefully reasonable sounding story on why this is intuitively a good thing to do. But of course, that's not a proof. And it's actually quite amazing that this story even works. I mean, what I told you, this can be made rigorous, and it took some effort to prove this result, that this minimum that comes from this optimization problem actually is asymptotically the log probability. So this was a sequence of papers that improved this deduction, this large deviation principle, starting with the result of Chatterjee and Varadhan, where they used Semirady's graph regularity method, which means that they can only do it essentially for p constant, or p decreasing extremely slowly, but I won't even mention like how slowly p, but essentially p constant. And then subsequent work by Chatterjee and Dembo manages to let p go to 0 like some n to minus small constant. And that constant has been improved recently by a paper of Eldan, and currently this is more or less the state of art. But we believe that this should go all the way down to maybe 1/2 or maybe even -1. Plus, maybe some extra log
like -1 log n or something.
Yeah, so exactly, some extra log factor. But that seems, I can only dream. So even getting it down to 1/2 would be a very big deal. I think that would involve some significantly new ideas to get this all the way down to 1/√n.
So if you get it to log n, will you get it to minimum?
Okay. So I'll just mention some of the methods that were used. So in Chatterjee Varadhan, Semirady's graph regularity method, and then Chatterjee and Dembo, so Chatterjee, in his PhD thesis, he developed this method called exchangeable, so Stein's method for exchangeable pairs. So it's an extension of the classical Stein's method that's proven very powerful, and this is, in some sense, an application of that method for this specific problem. And Eldan used a completely different method using stochastic calculus, stochastic control, and there's a lot of Brownian motion Ito calculus that were used to analyze this problem. Somehow he converted this problem to a continuous problem and then analyzed that problem. I can tell you more, but this is all very difficult work. Let me give you another interpretation of the story I just told you. So it's the same story, but just told in a slightly different way. Now, so there's a general principle in probability that if you have some probability distribution, this also applies for exponential random graph models, but essentially anything that should come up in nature. right, comes from some entropy maximization process. So you have some natural probability distribution. It should be entropy maximizing with respect to something, and in particular, the conditional probability distribution should be given by the entropy maximizing distribution. It's subject to, let's say, large deviation condition. Because that's just a general principle. What a large deviation principle on the last slide tell you is that whenever we prove this, whenever this holds, it tells you that for random graphs for this specific problem, we can approximate this distribution by an entropy maximizing product measure. Previously, it's an arbitrary measure, and this is telling you that the entropy maximizing measure is approximately a product measure over the edges. The edges, they should behave independently. That is not always true. You can easily cook up situations where this fails completely. But for these applications, for random graphs, for counting triangles in random graphs, we believe that under fairly generous hypotheses, this should be true.
You mean sparse as well?
Well, in the sense that whatever we can.
Here.
Yeah, that's right. So it's the same story, but told in different ways.
But when you when you need to plant a hub,
yeah,
that doesn't seem like the edges would be independent.
Well, when you plant the hub, okay, because I'm losing. So when you plant the hub, you fix the location of the hub. Right? Once you fix the edges, that should be part of your hub. Condition on that, then everything's independent. Of course, you can say, well, there's a lot of variation on where you put the hub in, but at an exponential level, that's a lower order term. You can also formulate this variational problem in terms of graphons or graph limits. So a graphon is a symmetric measurable function from the square to interval. Well, I'm thinking of this as, you look at the adjacency matrix from very far away. And symmetric just means w of x comma y equals w of y comma x. So this is the discrete variational problem I wrote 2 slides ago. So it's the same formula. And one can write down the analog for graphons, namely to minimize some entropy type quantity integrated over the graphon, subject to having enough triangles in this graphon sense. So this is meant to be a fairly straightforward translation. And the nice thing about this latter problem is that because of compactness results having to do with, so in the fundamental work of the Lovas and Chatterjee, where they showed that the space of graphons is compact under a natural cut metric, as a consequence, we know that this variational problem has a minimizer. So it says minimize, doesn't mean, initially you can only say inf, maybe you never approach the minimum, but because of compactness, there is a specific graphon that minimizes this one. Not necessarily. Often it is, not necessarily.
If it's convex?
Unclear. It's not clear what, because this constraint is not complex. So, and there are situations where there are some interesting situations where I have reasons to believe that it is not unique. So uniqueness is not necessarily the case, but often, generically, it should be true. In general, we have no idea how to solve this variation. Just because you can write it down and has nice properties doesn't mean that you can solve it, or even numerically.
Earlier Lagrange equation?
Sorry?
Earlier Lagrange equation?
So you can write down the Euler Lagrange equations, but can you solve it, right?
Sometimes.
Now you can always write down, constraints that are necessary for the optimum to be satisfied, but even if you give me a powerful computer, I'm not sure how to even estimate up to arbitrary precision this number.
But in this case, it's integral equation. It's non-linear integral.
It's not exactly, yeah. Right. So this variational problem has a minimum, has a minimizer, not necessarily unique, but let's say it's unique just for clarity. Let's say it's unique. What does the minimizing graphon represent? it represents the most likely graphs to occur conditioned on the rare event. So in other words, this is the cause I tried to tell you about earlier. So if you know what the minimizing graphon is, you show me the minimizing graphon, that is the story for how large deviation occurs. And replica symmetry, meaning uniform boost in edge density, corresponds to having the constant graphon being the minimizer of this variational point. And when that occurs, that means that the conditioned random graph looks like Erdos-Renyi. So uniform boosting edge density. So let me tell you what specifically now what the results are. In the sparse setting, P probability goes to 0, perhaps slowly as a function of n. The order of the rate, the order of the log probability was determined only a few years ago. And okay, here's a formula, the specific form, don't worry about it too much, so let me tell you the story. In other words, a very easy proof of the lower bound. The upper bound is the meat of the work, but the lower bound is easy. The lower bound comes from forcing a clique. So you force a clique of the right size to be present, and there are enough triangles in this clique, and that's good enough. Okay? So then the probability that you see this clique is just p raised to the number of edges you need to embed. And you work out the parameters and easy calculation, and that's what you get. So that part is easy. Getting the other direction, that was the infamous upper tail that was resolved. Now we're interested in getting the right constant. Right? So what is this constant? And here is the, this is the state bar. Right? So this is now what we know. For P, at least, essentially n to the minus 1/18th, we know that that is the right constant. Again, that's the formula. Don't worry so much about the formula. Let me tell you the story. Right? What do these numbers represent? Easy proof of the lower bound. Same story as in the last slide. You plan a clique, but now because I care about constants, I need to be a little more careful about how to do that calculation. But it's not hard. We just, instead of writing down just some arbitrary constant here, you figure out what the constant should be. How many new vertices and how many new edges do you need to put in to get enough triangles? Okay, you work it out, and that's what comes out. So it's delta 1/2 delta to the 2/3 in exponent. But you see, there's minimum of 2 terms. So this is not the only story. Turns out there's a different story that is also competitive. You can plan a hub, putting an even smaller set of vertices such that every vertex here is adjacent to everything else in this graph. Okay, you can easily work out what is the right number of vertices to put in here to get you enough triangles, and that is the second guy. When delta is bigger than 27/8, the first guy is, this number is smaller. That's where the threshold comes from. So this is exponentially more likely. And when delta is less than 27/8, this possibility is exponentially more likely. Now, I have to say that even though we have figured out what the right number is here, I cannot, in a rigorous mathematical sense, tell you what the conditioned random graph looks like. So here's sort of a theorem I would like to prove, but I don't even know how to phrase a conjecture. I want to say something along the following lines. Condition on, let's say, I have at least twice as many triangles as expected. Can you describe this conditioned random graph? What does the typical conditioned random graph look like, conditioned on having way too many triangles? Now, intuitively, I know that it should look like one of these things, but I don't have a good way to even state a conjecture which formalizes that notion.
Basically, you want something like in the dense case where they say that, okay, the CRGM with that many triangles looks like GMP.
That's right. Yeah, so I want to say, suppose I'm in this regime, if it has too many triangles, conditioned on that rare event, I want to say this graph looks like some GMP with some planted clique. Of course, you can vary a little bit, right? It's not a full clique. You can let it be a little bit rough. But how do you even?
Because outside of the clique, it didn't do anything, so it should look like GMP modified with this.
That's right. That's right. And the reason why I don't have enough tools to do this is that the size of this clique. Now, remember, p goes to 0. Right? So the width of this clique, the fraction of vertices involved goes to 0. So the usual notions coming from graph limit theory, like cut norms and whatnot, do not detect this clique. They don't see the clique. So the usual classical notions.
And even not different types of notions. If you try to formulate this in a more, like these exchangeable graph fonts or LP graph fonts, that doesn't.
Yeah. So in fact, LP graph fonts, at least in the version that was in my paper with Kong, Chase, and Bork, the very notion of LP graph fonts was designed to prevent this from happening. Right? So it was designed to not allow dense spots. Right? So it's very much orthogonal to what we're trying to do here. Yeah, so another major.
Yeah. What is this? What is this? No, can you comment?
I'm working on it.
No, but can you say where it comes from? This 1/18?
It comes from Eldan's methods.
Yeah, but there's no sort of. It's just a number that pops out of the analysis. Not that there's some intuition behind it. It's like.
I don't know a good story around it. I mean, I'll say a little bit towards the end. What are some of the things involved and what could be possible bottlenecks? Okay. But I don't have a good story to tell about that. Yeah, same picture but in graph fonts. So planting a clique versus planting a hub. And okay, just to mention that here I've stated it for triangles, but we also know it in general for every graph. Instead of counting triangles, counting every graph. And there, it's similar types of results, but you get a different number up here. Let me just show you some examples. So here's the result. Again, you have some number related to how the quality of this result. So there are 3 edges, like in a triangle, then 1/18, but otherwise 1/6 times the number of edges. Some constant, this constant, let me just show you a few examples. Like in the last slide for a triangle, this is a constant. For cycle, again, it's a minimum of 2 different expressions. For K4, it's a minimum of 2 different expressions.
Is it always a minimum of 2?
If it's not regular, right? So if the graph is not regular, then it's just 1 expression.
Oh, but it's never a minimum of more than 2.
Right. Here's.
Oh my God.
Right, so it's not the kind of numbers that before working on this problem, you would never expect this kind of numbers to pop up. But they do.
But this number is not nice.
It's
nice. Not good looking number.
So in some sense, I don't really. I show you this because it's maybe a little bit surprising looking at this number.
Yeah.
This form. But actually, the story is the same as before. Namely, that the story is you either plant a clique or you plant a hub. And it turns out that when you are regular, both cases are competitive, just like with triangles. When you are not regular, right? So when you're like either of these 2 guys, then planting a clique is never optimal. So you always just want to plant a hub. So there's some specific formula coming out of the independence number of the polynomial, but I think the story I told you is more interesting. I'm currently working on extending all of this to random hypergraphs. So this is ongoing work with Yang Liu, who is an undergrad at MIT. So instead of random graph, look at a random k-uniform hypergraph. Let's say fixed k, for example, k equals to 3, meaning I look at all the triples on n vertices and I include every triple with probability p. You can ask the same kind of questions. I fix a H. What can you say about upper tails of H densities? And there, I think more varied phenomena could happen. Right? So there are different ways of embedding extra edges. For example, as before, you can plant a click. But planting hubs, there are now more variations of how you can plant a hub. I can plant maybe what's called two hub, meaning put down a set of vertices, and I include all triples that have two vertices in this hub. Or one hub, right? All triples with at least one vertex in this hub. And it's likely the case, I don't have any specific examples, but it's likely that we strongly believe that it's the case that there's some H for which the optimum graph could be a simultaneous overlay of these constructions. Right? Somehow you, at the same time, you put down a clique, embedded inside the clique there's a two hub, and inside the two hub there's a one hub. So it's a much more varied structure. So currently we understand what happens when H is a clique. And there are other possible constructions we're not yet able to rule out. But when H is a clique, it turns out only the first and the third possibilities come up. But for other H, we have reasons to believe that you could have a simultaneous overlay of everything altogether. So it seems to be a lot more varied possibilities. So this is ongoing work, so hopefully in a year or two I can tell you more about I hope more interesting diverse phenomena that could come up in random hypergraphs. There's another project I did with Bhattacharya, Ganguly, and Zhao. So instead of looking at random graphs, now I'm looking at an arithmetic setting. So in numbers 1 to n, I count the number of k-term arithmetic progressions. And so kind of like counting structures, but instead of counting triangles, I count some kind of solutions to arithmetic patterns. And we're able to derive similar set of results. I won't get into details of all of this, but the lower bound as before is easy lower bound. You plant an interval which plays the role of a clique. And as before, this is suboptimal, and improving this range now actually involves even maybe more interesting mathematics having to do with arithmetic combinatorics, understanding some number theory that go into this as well, instead of just graph theory. In the dense setting, so the question was, do you have replica symmetry? If you have GMP, G instance of GMP, condition of having too many triangles, let's say at least as many triangles as a typical GNQ, is this graph G close to GNQ in cut distance? Cut distance, it's not so important. You know what cut distance is for what I'm about to say, but just to be specific, it means that locally, if you put down for every set of vertices U, the number of edges of G in U is roughly what you expect. So that's what it means to be close in cut distance. So you can ask, do you have replica symmetry or do you have symmetry breaking? Does this large deviation event come from a uniform boost in edge densities, or does it come from some other reason? So that was the question. Does GMP, conditioned on having too many triangles, look like GMQ? So we were able to resolve this question, and this is what the answer looks like. So there's a phase diagram. X-axis is P, y-axis is Q.
Is it in your paper description?
Yeah, it's in my paper. So if your P and Q is somewhere in here, then the answer is yes. If you're in the red region, the answer is no.
And do you know what happened in the red region specifically?
We do not know what happens. We just know that it is not replica symmetry. But we do not know, and in general, we have no method of solving. So you give me a PQ in this red region, and ask me to go home and tell you what the answer is, I don't have a method.
You don't come back.
Exactly.
Do you even have a conjecture, like?
There are some conjectures. For example,
or simulation?
So here are a couple possibilities. So even running numerical simulations, and there are people who do this. It's not entirely convincing. Like what the I think I would entertain a couple of possibilities. One possibility is that in the node region, what I just see is a two-step block model, a stochastic block model, two-step. A second possibility I'm willing to entertain is that as you go deeper and deeper into the red region, as you go closer and closer to the vertical axis, the number of blocks goes up. That there's further filtration inside the red region.
How is this related to the work of Varadhan and Kenyon?
Yeah, so it is very much related. So they work on a similar, they work on a related problem where instead of conditioning a large deviation, they hold edge density and triangle density fixed, and ask what does the typical graph?
Microcanonical versus.
That's right.
Versus
So that's
canonical.
That's right. So this is the word they like to microcanonical versus canonical. Yeah. So grand canonical. And so this is what they're looking at, and there they have some rigorous results on a very small region, very small region, and they have lots of numerical results.
Which also sort of support that it might be true as you move.
Right. But when you get in there, the numbers are very small. And I'm not sure I trust the numerical calculations. But I'm willing to entertain both possibilities.
Phase transition was going on the line.
On the line, it's still replica symmetric.
So there is no phase transition.
Well, I mean, it's I guess it depends on what you mean by it's continuous.
So it's continuous, no.
But the derivative might not be. Okay, if you replace H from a triangle to some other deregular graph, we have pictures to tell you what a boundary is. So for two regular, like triangle and cycle, as in the previous diagram, so it's that boundary. But if you're looking at a click on 4 vertices, that's 3 regular, the boundary moves right. Well, we can prove this boundary. Everything to the right is replica symmetric, everything to the left is symmetry breaking. Similarly, the people care about eigenvalues, right? If you give me a graph GMP and write down its adjacency matrix and ask what about its top eigenvalue, typically it should be around its average degree, NP. So you can ask what happens when it's much bigger than NP? What happens when it's NQ? It turns out you can write down the problem more or less the same way, and the solution is the same as the D equals to Q, D equals to 2 curve. It's a triangle curve. It's the same boundary. And somehow this is not that surprising. And let me try to explain why this is not that surprising. You know that the top eigenvalue is given by cycle counts. Top eigenvalue dictates long counts of long cycles. And although this is not a proof, but if you know that all the cycles have the same phase boundary, it should not be that surprising that the boundary for the phase diagram for the top eigenvalue should be the same as well. It requires a proof, but it's not that surprising. When H is irregular, for example, even a path on 2 edges, I don't know what the boundary is. I cannot prove this boundary. So somehow this is an accident that we're able to solve this problem for deregular graphs.
It's actually, can you explain why it doesn't matter what this deregular graph is?
It turns out the proof and the construction only depends on the deregularity. So I don't have a good intuition. I guess, I don't have a good way to tell the story. For lower tau, I think there's also an interesting open problem. So lower tau meaning below the diagonal. I was able to show some region of replica symmetry, some region of symmetry breaking, and as you see, there's a gap in the middle that I do not know how to prove. And in particular, there's even a gap in the slope.
Is it where they have these scallops in the microcanonical ensemble?
The scallops correspond to what happens very close to the right-hand side.
Yeah.
So there's a scallop, but that's, I mean, the shape of the scallop is known. What happens in terms of entropy, that is not. Yeah, now a lot of what I tell you has analog in that world as well. Tell you this.
Sure.
Okay. For example, you can ask, what about large deviation in the lower term? If your number of triangles is less than expectation by a delta fraction. When delta is 1%, I can prove that there is replica symmetry. When delta is 99%, I can prove there's symmetry breaking. But I don't know where the transition is. There's a critical delta. I don't know where that is. I mean, I cannot prove that there's only a single transition. It could be that it goes back and forth, but that seems unlikely. I'm willing to bet that that's not the case.
No, but this cannot be right? So like it can be 0, 1. So like you do have some upper.
I mean, yeah, exactly. This is just some record. Yeah. There's some specific numbers.
Right, but,
let me skip this. So this tells you, what is this curve. So previously there was some formula, but it comes out of some. So it has to do with the convexity of this function, this relative entropy function. And so basically, this curve corresponds to places where that function is not convex. Now, so I promise I'll tell you something about exponential random graphs. Because here's the thing I'll tell you about exponential random graphs. So first of all, let me just set it up. So a random graph G, so it's a model for generating a random graph G on n vertices, where G is chosen with probability proportional to some exponential e to the h. I know people like to use minus h for Hamiltonian, but it doesn't matter. So some examples, if h is just a constant, then this is the same as gn1/2. So every graph occurs same probability. If h is linear in the number of edges, then this is just GNP. So work out, there's a specific relationship between beta and p. So the more interesting cases is when you add on some extra parameters corresponding to other graph statistics, such as the number of triangles. So when you tack on this extra term, then in some sense you're saying I'm preferring graphs with more triangles, or I'm preferring graphs with fewer triangles, depending on which way the coefficients go. One motivation for these exponential random graph models is that people think of them as a way of generating graphs with, let's say, more triangles. And it has a nice property where there's a natural Markov chain mixing, there's a Markov chain Monte Carlo MCMC for sampling a random graph under this model. Namely, you start with, let's say, any graph, and then you flip an edge according to what the condition probability of that edge appearing is under your distribution. So you can continue this process and sample from this distribution. But I've just described to you a process. There was no proof that that actually works. So does this work? Does this MCMC converge to the desired distribution, and how quickly does it converge? And that's, I think, an important question. You have this model. The intention of this model is to generate. Can you do it? And there's a paper of Amidi, Bressler, and Slide that actually is very negative on this issue. Namely, at least when beta is non-negative, they prove that there's some regimes. In the high temperature regime, the mixing time is reasonable, but the graph that you end up generating, even though it comes from exponential random graph model, it is not appreciably different from the A-ish radiator. Somehow you don't get a new phenomenon. You might as well just sample GNP anyway. And there's also regions where the mixing time is exponential. And Chatterjee and Diaconis furthered this line of work, similar to this result of graph limits, using graph limits to do large deviations. And they showed that this Ergon, this exponential random graph model, can be analyzed via a graph on variation problem. And this is seen as a weakness of the model. So somehow I think when this paper came out, all the subsequent papers came in and said, well, okay, we have this weakness, then at least in the dense regime, this model is kind of not useful because it doesn't get you what you want. It's intended to get you some different model with lots of triangles, but ends up just getting you a different GMP. And so Eyal, Lubetsky, and I, so in the same paper where we had this nice pretty picture with the phase diagram, we found out that actually that's not a complete story. It's not that this model, I think somehow this previous paper was a bit dismissive of the entire approach, but it turns out if you add even just a little exponent, simple alpha, then it changes the story dramatically. When alpha is less than 2/3, you do get non-Eldan behavior. And this picture I showed you earlier, it turns out to correspond to the statement here about alpha less than 2/3. So let me explain what I mean. So when alpha equals to 1, so that's the old Ergon model, in this entire picture, there is no symmetry breaking behavior. So everywhere here looks like GMP for some key. But as you decrease alpha below 2/3, it turns out that for various parameters of beta 1 and beta 2, in the red region, you have non-Eldan behavior. And that corresponds to, you can think of the red region as some transformation of this red region. So that red region is some transformation of this red region. And just like how we do not know what the typical graph here looks like, we do not know what the typical graph there looks like. But at least it's not Eldan. So the hope is that this observation will help at least reignite interest in that model, that it's not completely useless, but one just has to give it more variation and revive the model to have more interesting phenomena. The last thing I want to mention is the relationship between Ergon's exponential random graph models on one hand and large deviations. And you can see a lot of the papers I cited, it's the same papers that analyze both or the same set of authors, and that's because these two are at the heart the same problem. Estimating the partition function is closely, of this Ergon, is closely related to sampling. And estimating the partition function also allows us to obtain large deviation results. Namely, if one of the first things you learn is in high-dimensional probability is Chernoff bounds. And the way you prove Chernoff bounds is to take an exponential moment-generating function. And this is really the only way, in general, how I know how to prove large deviation type results. And it corresponds, for example, if you want to estimate large deviation on the number of triangles, then I'm trying to estimate this quantity here. So try to estimate sum over all the probabilities over graphs, obtaining some large deviation. Then I can rewrite this as some other form with this quantity, essentially, this is basically 1 when I have large deviation, and it's negligible when I don't have large deviation. But then this whole expression is just some exponential quantity. And that's what happens in the Ergon. So estimating this partition function of the Ergon allows you to do large deviation. And recent advances allow us to estimate this partition function using difficult but powerful methods, but not entirely lossless. For example, this step, so you're asking where 1/18th comes from. Part of the loss comes from using that. This is potentially quite lossy, but there are other places that are lossy as well. But it's just very difficult in general to get a hold on one hand estimating that, but two, somehow transforming the large deviation problem to the partition estimation problem. Okay. So to wrap this up, so I told you this was a survey of recent developments in large deviations, exponential random graphs, and we now have a much better understanding compared to before of what the typical large deviation looks like, but still lots remain to be done, both in terms of developing general tools for estimating large deviation, even in random graphs, but also solving the variational problem. Thank you.
Thank you very much for this very clear talk on these subjects, not to be complicated. Any questions? Please? Okay, I have just one. Sparse Ergon. So what is because I can so what are the results on sparse exponential graphs? Right,
so sparse, yeah. So sparse corresponds to
essentially that
rescaling. So basically, letting your beta go to.
So we are in the phase space. Then where? In the phase space.
To the right, we're going to.
So it's a little bit.
Yeah.
One has to rescale everything. Right? So it corresponds to not taking constant beta,
Right.
but so it corresponds to, let's say, taking increasing beta. And there, these methods of, let's say, Chatterjee, Dembo, and Eldan allow you to estimate what happens for sparse exponential random graphs. So their techniques allow you to estimate this quantity, which is in the entire route. I mean, this is how they managed to prove principal theorems for large deviation. So it's possible, but I don't know any specific results on. So I guess one thing I can say is their results, whenever they hold, tell you that the exponential random graph approximately decomposes as a product measure, or as a mixture of product measures. So now you can view the edges independently. And then the rest of the question is how do you, what do you put as the individual edge probabilities? And that's the variation.
But they didn't solve, right?
They don't solve. They don't solve.
They didn't solve. For the dense case, I know it's GNP, but for the sparse case, when I have a fixed number of edges, I don't know what that's.
But you know that it's
From that paper.
but you know that it's, you assign a different number to every edge.
Any questions? Any other questions? No? Okay, let's thank Yufei again.